Okay, so hello everyone. Homework's due tonight, don't forget it. So if you haven't started it, then it's high time to start working on that. Right, so Ryan asked me to clarify a question about duality. Can you see? Yeah. So if you have constraints with equalities, such as, Ax is b, then you can rewrite this as Ax minus b equals 0, or you could also say that b minus, Ax is 0, right? And when you write the Karushkun-Tucker conditions, then you might wonder whether it leads to different dual functions or not, or the solutions will be different or not. But apparently the solutions will be the same. So what you just have to consider is that in the in one case you would minimize the function f over R to them, and if you so say in this case, in the other case, you would minimize something like this over R to the n. So the value of the solutions apparently would be the same, except how you parameterize these solutions, that would be different. Do you want to add something more, or?
Just to give a brief context, this was the question when somebody asked if you had conjugates. Remember, we had in one way we had like a conjugate of a variable plus a conjugate of a negative variable. But had we done this equality constraint the other way around, like Barnabas wrote, we would have gotten like different signs within those conjugate functions. And somebody asked are they the same, and they're not the same function. It's just like you said, it's just two ways of parameterizing the same problem. I can write any optimization problem that's unconstrained that's minimize f of x or minimize f of minus x.
Right, so those two functions are not the same, but still we would get the same solutions. Okay, so last time we started to talk about interior point methods, and this is what we are going to continue now. So we started with the linear programs, and we discussed that there are two ways to think of linear programs. One of them is that linear programs are continuous optimization problems. The other is that linear programs are just a linear program is just a combinatorial search where your constraints define corner points, and you want to find that corner point where your cost function has minimum or maximum value. And then we discussed the history of linear programs a little bit. We were discussing that for a long time people didn't know about the runtime complexity of the simplex method, and they were wondering whether it's polynomial or exponential. First they thought it's polynomial, then they thought it's exponential. Then someone proved that there's a worst case, there are worst case problems where the running time is exponential. Then in another result, people showed that, okay, if you found a bad example, still if you perturb a little bit the parameters, tiny bit, then you would still get a problem where the running time is polynomial. Right, so you remember this was the bad example where the running time was exponential. And then people were wondering if it's possible to always construct algorithms that running time is always polynomial, and then we discussed that there's such algorithms, and the first algorithm was this ellipsoid method. And for a simplified version of the ellipsoid method, we proved that its running time was polynomial. And how we did that? That instead of solving a whole linear program, we just solved this feasibility problem. And the idea was that, so our goal is that there is this set omega that's defined with linear constraints. Our goal is to find a point in omega. And what we did, that we put a big ball on this set omega, and in each time step, we shrinked this ball to an ellipsoid. The ellipsoid was smaller and smaller, but in each time step, this ellipsoid constraint omega, we also assume that there's a ball inside of this set omega with radius little r. So it means that the volume of omega is bigger than the volume of this ball. We also proved that in mstep, the ellipsoid method either stops, big O m steps, the ellipsoid method either stops or reduces the size of the ellipsoid to half. And as a result, we proved that we are here. That in m squared log capital R over little r steps, the algorithm has to stop, the ellipsoid method, and in each step of the ellipsoid method, we have m squared extra calculation. So that's why, because of that, it doesn't work. So because of that, the whole running time was, if you remember, was m to the 4th log r over r. Oh, and for the, right, and for this problem, we had how we wrote the running time. I think it was in this form, m plus n to the 4th. Right? So for general LP, what we did, that we showed that it's enough. If you want to solve a linear program, general linear program, then it's enough to find a feasible solution for this problem. And the solution of this problem would be a primal dual optimal problem for the linear program. That's where we stopped on Tuesday. So I'm wondering who has questions, or what was not clear, or where did you get lost? Yes?
Well, how do we find the initial ball?
Yeah, that's a good point. So we didn't discuss that. So we just assume that, hey, it's given to you. If there are algorithms that can do that, but they are more complicated. So for this algorithm, we need an initial ball that contains our set omega, and we also assume that we know this the radius of this small ball inside of omega, and it's also a good question, how do you know that? Right, so there are more complicated algorithms that can handle that, but this one cannot do that. And also this rate, it's not optimal either. So there are algorithms where here they have 3.5. But those are more complicated too. Yes?
The formulas in slides 22 and 23, the actual formulas for the ellipsoid, are those easy to prove? Like, should we be able to derive them?
You should be able to. It's just lots of calculations. So it's a couple of lines, but they are not difficult at all.
Okay.
So if you are interested, I can give you pointers for those calculations.
That'd be great.
Other questions?
So in the original drawing, you showed that the set was like concave. In the proof, we assumed that the omega was linear, right?
Yes. Oh, and that's also a good point. So there are a generalization of ellipsoid methods with more general constraints as well. So we will discuss one now. Other questions? Questions? No? Everything is clear? So you can say that, hey, I got lost. I don't know what you are talking about. That's fine too. No? Okay. Right? Or you can come to my office hours too. That might be useful. So let's move on. So now we discuss a more general problem using ellipsoid method. And here, we want to minimize a function f naught, which can be a general nonlinear cost function. So in the previous case, it was a linear cost function. And we do the same thing, that we assume that there's a epsilon naught set, which is, again, big enough in that sense that the optimal solution x star of our problem will be in this epsilon not big enough ellipsoid. Okay, and of course, we assume that this epsilon naught has two parameters. It has parameters p naught and x naught, and we assume that p naught is positive definite matrix. And we do the same thing, that we do this ellipsoid method that always contains x star, and at iteration k, xk will denote the center of this ellipsoid. Pk will be, again, the parameter matrix of the ellipsoid. And we will assume that x star is in this ellipsoid at step k. And now the question is how to construct an ellipsoid at time step k plus 1, which will be smaller than the original ellipsoid and still contains the solution. Does it make sense? Right, and one observation that we can make, that the subgradient can be useful for us. So if, say, gk plus 1 denotes the subgradient at point xk, then by the definition of the subgradient, we know that all points, in every point, the function value, so say point y, the function value will be larger than this quantity. That's the definition of subgradient. as a special case from this, if I write x star as y, we will have that the inner product between the subgradient and this difference will be smaller or equal than this expression here. And since x star is our optimal solution, this will be non-negative. Is it clear? If it's clear, then do this. Okay, if it's not clear, then do this. Okay, so now the key step is if we have access to this subgradient at point xk, so if we have access to this vector gk plus 1, then it can be used again as a normal vector of a cutting plane. So we can repeat the same thing that we did in the for linear programs. Right, so we just discussed these first two lines in this slide, that x star is in ellipsoid epsilon k, which is defined by this expression. And we just discussed this inequality here, that the inner product of the subgradient with this difference is non-negative. And now the key step here is that we know that x star is in the ellipsoid k, and we also know that x star is in this half space here because of the property of the subgradient, right? So if you replace z with x star, then you would see that it's non-negative. And this is a half space. So what we do is that we have epsilon k, we calculate this half space, we intersect that with the ellipsoid, we got again a half ellipsoid, and we fit a new ellipsoid to this half ellipsoid, and we stop if this difference is smaller than epsilon, or say your function value doesn't change much. Okay, so here is what happens in practice. So we start, you can see the level sets of the function we want to minimize, and we start from a point x naught, and we have a starting ellipsoid, and we calculate the subgradient in this point x naught, and that defines, so this is the subgradient vector that defines this half space, right? And we calculate the intersection of this half space with the original ellipsoid. That's this half ellipsoid here. And we fit a new ellipsoid to this intersection. That's this, and we repeat this process again. So in the second step of the iteration, we calculate the center of this new ellipsoid. We are in this point, calculate the subgradient there. That's the subgradient. That defines this half space. We calculate the intersection of this half space with our ellipsoid. Then this will be the half ellipsoid. We fit a new ellipsoid, and so on. And you can see this ellipsoid shrinks, gets smaller and smaller, and see at iteration 5 we are here. So what you need is to have access to the subgradient. And in some problems you have that, some problems you don't have that. Questions? Anyone? So it's clear? Good. Right, so I wrote the update rules for this ellipsoid here. They are a bit ugly. It's not so difficult to prove them, but we don't have time. So here is what happens. So xk is the center of the ellipsoid, at step k. This is the new center of the ellipsoid at step k plus 1. Pk was the parameter matrix of the ellipsoid at step k. And we will use this g tilde k plus 1, which is defined by this expression. Is just the subgradient divided by the strange norm of the subgradient, where we have, I missed the pk here. Okay, and n is the dimension. So anyhow, the point here is that there's an algorithm that can fit ellipsoid to this half ellipsoid. Okay. So this is the general idea of cutting planes and ellipsoid methods. Here the problem was unconstrained, but there are cutting planes method for problems with constraints as well. So what do you think what you should do that in that case? So if you have some constraints, how would you modify the ellipsoid method?
Do projection at the end of each iteration.
Yeah, so you can do projection. Another thing that you can cut with those constraints as well. So you have the ellipsoid, and if some part of the ellipsoid is outside of the constraints, you just cut that out and you fit a ellipsoid to this new set, right? So in each step you fit an ellipsoid. Some part of the ellipsoid might be feasible, some part is not feasible. If it's not feasible, you cut that out. But you are right that you could do projections as well, of course. Yes. Okay, so the title of this lecture was interior point methods. But if you think about how we solved, say, the linear program with ellipsoid method, it was not really interior point method in that sense that we were approaching the solution from a set that was larger than omega, not inside of omega, right? But what we are going to do now is to discuss. So still some people call these interior point methods, but now we are going to discuss penalty functions and barrier functions. And there are some people who call only the barrier function methods interior point methods. So let's go there. Just a summary of this lecture. We discussed linear programs, simplex algorithms, and then we saw this Cremint example as a problem where the running time of the simplex algorithm is exponential. Then we discussed these cutting planes and ellipsoid methods, how to solve LP. We proved that it has polynomial rate, and then we discussed briefly how to use these ideas to solve unconstrained problems as well. Right, and what we are going to talk about today is, again, penalty and barrier functions. If you want to read more about these problems, I really recommend you these books. So here is the problem that we call primal problem. We want to minimize a function over a set S. We assume that this function f is continuous, and the problem is an n-dimensional problem. And what we do in penalty method, we define a penalty program that replaces the original problem with this one, where this is called penalty term. So here C is a positive number, And P is a so-called penalty function that maps n-dimensional vectors to real numbers, and it has these three properties: that P is continuous, that simplifies our life. We assume that P is non-negative for all vectors in the n-dimensional space, and Px is 0 if and only if x is feasible, so x is in the set S. So what happens here is, if x is not in the set S, then we suffer some penalty. Right. So as a special case that we will consider is when the set S is represented with these equations. So there are, say, P functions, G1, G2, and so on, Gp, and our constraint is that they are non-negative. And what would be a useful penalty in this case? So we should suffer some penalty if these functions are positive, right? So useful penalty is that let the penalty function P be, say, the maximum of the sum of these expressions, so the positive part of the functions. Right, and you can square it or put some other power, it doesn't matter. But the point is that we don't have any penalty if these functions are non-positive, right? So as an example, let's say G1 function be x minus b, G2 is x no, that's not good. So what I want is that that I want to represent these sets that x is between a and b. So what I need is that G1x be x minus b, and say G2x a minus x. Right, so this is how it looks like, the penalty function if I change the values of c. So if I increase c, I suffer more and more, larger and larger penalties if I'm outside of this interval. Right? So again, my constraint set is that x is between a and b. Yep. Exactly. Yeah, that's good as well. We will come back to that a bit later, right? But it's kind of similar, like why you use ridge regression when you can use, like, you can use L1 penalty, L2 penalty, and many other problems as well. And the effect of this is similar. So what, in our point of view, we will come back to that. You can choose any power that's larger than 1. We will have some difficulties if that's smaller than 1, though, because we need to calculate the gradient of these functions at some point. But you are right that it could be any power. But let's discuss that later. So what we want to prove is this, that if you increase c, so if c is going to infinity, then the solution of this penalty problem that we just defined here, so it's denoted with PC, the solution of this will converge to the solution of the original problem. That's our goal. Question? No? So here is then my question. So what would you do if our constraints look like this? Let's say GIX is non-negative, and I have some equality constraints as well. So say HJX is 0. So how would you use, what would be a good penalty function here, or what would you do? Is the question clear? So instead of just inequality constraints that we had before, now we have equalities as well. Yeah, that's good. So we can have the original penalty and add hj squared. Yeah, that's used quite often. Right, so I can have the, say, previous penalty that we had plus the sum of, right? Other solution? Yeah, and other solution then writing Q here. Okay, so sometimes what people do is that they just rewrite H like this. And they treat as we treated J before. Okay, so here is how the penalty method is defined. So we first define C1, C2, and so on, CK plus 1 positive numbers that diverge to infinity. And the penalty program is QCX is defined as f of x plus c times px, and xk is the point that minimizes this penalty program. Okay, so again, this is just okay, so this is called penalty program, and there are 4 important properties. So the first one so the algorithm is clear, right? You set up C numbers and you minimize in each step this. And now I ask a couple of questions. What's the relationship between these? You should guess. Which is smaller? Which is bigger? Can we compare them? Who thinks the left side is smaller? 1. Who thinks the right side is smaller? 3. So there are 4 people in the class. So remember, the original problem is we want to minimize our functions, right? Okay, now you've got enough time, so let's try again. Who thinks the left side is smaller? It should be a clue that even I'm saying. Right? Okay, who thinks that the right side is smaller? Still people don't believe me. Huh, interesting. Okay, so the left side will be smaller. Okay, second property, we will prove these things. Second property, so if I just compare the penalties, it should be easier, but what do you think what's going to happen? Which is smaller, left side or right side? Right, so what we want is that how the algorithm proceeds, we should suffer less and smaller penalty, right? Okay, here is a question. Which is smaller, left? Oh, your left is different than my left, right? So, which is smaller, f of xk or f of xk plus 1? Who says f of xk is smaller? And who says f of xk plus 1 is smaller? Right, that's the majority because we want to minimize f, right? And you are wrong. So this is what happens when we use these penalty functions, that also we want to minimize f, we will approach the minimum from the other direction. So we run this iteration, it will be bigger and bigger. You remember that now how xk is defined using this penalty function. That's why it's weird. And finally, the fourth property is that f of x star so this is what happens during the algorithm, that we generate new points x1, x2, xk, right? That's f of xk. And we calculate this value in the penalty program, that's q ck xk. Right? So actually what the algorithm does, the penalty program, that it minimizes this function in x, that will be xk. And this is always less than x star, but in the next iteration, this guy will improve. And we converge to f of x star. Yep. Shocked? Surprised? We're minimizing q. That will be xk. But ck plus 1 is bigger than ck. Right? So xk is the minimum of q ckx. That's xk. Next step, we have a new ck plus 1, which is bigger than the original ck. We minimize the new q function. We get a new xk plus 1. But we got that with a bigger c. That's why the q is actually increasing. I couldn't hear you.
In the fourth part of these lemmas, if x star is the optimal, by the fourth lemma, we know that xk was more optimal. And so
X star is the optimal of the original problem, where the primal problem. And we want to converge to that using this penalty method. xk is the optimal solution of the penalty method at time step k. So that xk minimizes, it's here, function q.
I think what might be confusing is that the fourth lemma implies that f of xk is smaller than f of x star.
Right.
The key is that xk is not feasible, so it's possible for it to be smaller.
Yeah. Right. So if it was not clear, we solve constrained optimization now. Good? Do you need more time or it's okay now? I want to move on, but okay. So first statement, q, c, k, x, k. So this is what we want to prove. The proof is really very simple. So q, ck plus 1, xk plus 1, by definition, is just f xk plus 1 plus ck plus 1 times the penalty at xk plus 1. So this is the definition of q at xk plus 1. And we know that this is bigger than if I just write ck here, right? Because ck plus 1 is bigger than ck. And I claim that this expression is bigger than this. Why? Because that was the definition of xk. Xk is the expression that minimizes this, right? And what's this expression? This is, by definition, q, ck, xk. Good? Okay, let's move on. We want to prove this. So again, the proof is like 3 lines. So let me know if I write something not good. I claim that the left-hand side, your right-hand side, right? So this is clear, right? Again, because we just proved this, that xk is the minimum of this. So if I write xk plus 1 instead of xk, this is bigger. And I can do the same thing with xk plus 1. So f xk plus 1 plus ck plus 1 . Oh, break time, but we finish this first. So, right? We have these 2 inequalities. So tell me, what should I do now? And then you can have a break. So we want to prove this line from this too. Sum. Okay, let's try that. So if I sum these, then what we would get, ck pxk plus ck plus 1 pxk plus 1 is smaller than, but not bigger than, ck pxk plus 1 plus ck plus 1 pxk. Okay, next step. Subtract. Okay. ck plus 1 minus ck pxk, right? And we know that this is positive, pxk plus 1 smaller than pxk, right? Good. So let's have a break now, and in the break you can try to prove the other two lemmas. Stop you doing your homework now. So let's continue. Okay, so the third lemma is that we want to prove that f of xk is smaller than, or at least not bigger than, f of xk plus 1. So what should we do? So this is what that lemma that was very surprising to some of you. Right? We do the same things that we have done. So we know that this is bigger than what? Xk plus ck, good, pxk, right? And we know that this is bigger than pxk plus 1. Good? Okay, so, and there's the fourth lemma that so this is the optimum of the primal problem, and we want to prove that f of x star is bigger than q ck plus 1. So we already proved this one, right? That was the first part, first lemma. Okay, so f of x star is f of x star plus ck p x star. Why? Because this is 0 since x star is in the set S, right? So what should we do now? I hope you are tired of this now, but we just do what we always do. CKP xk. Right? Because xk again minimizes this function, not x star. This is q ck xk. So this proves that f of x star is bigger than this. And all that left is to show that this is not smaller than f of xk. And why this is true?
Penalty, so it's
Yeah, penalty is non-negative, ck is positive. Good? Right, so after these lemmas, we can state the penalty convergence theorem, which is the following, that suppose that f, g, p, they are continuous functions, So xk is the output of the penalty method. We define these C numbers that diverge to infinity, and let x bar be an arbitrary limit point of this series xk that was just generated with the penalty method. So what's our statement now? So it's clear what limit point is, right? So you have a series, it's clear what's the limit point of that. So what do I want to state now? What can we say about x bar? So it's clear how x bar was generated, right? So you run this penalty method, you got x1, x2, x3, and so on, vectors. We choose a limit point of this. And indeed, x bar solves P, the original problem, right? Where P was like this, that minimize f of x such that we have these constraints. Okay, let's try to prove this. So x bar is a limit point. It means that, so limit point of xk, it means that there's a set of indexes, say capital or calligraphic K, such that this x bar is the limit of these xk's. Okay, so we know that was our assumption that f is continuous. So therefore, what is this expression? So xk is going to x bar, f is continuous, then f of xk is converging to f of x bar. And let's define q star as a limit q ck xk. Why does this limit exist? Yes, and we proved that it's monotone, right? So, and it's bounded. And we know it's bounded by f of x star. Right, so maybe I'll just write this as f star. So this by definition is f of xk plus ck p xk. Right, we proved this one in lemma 4. Okay, so from this, q star is the limit of f of x k, k in k, plus the limit ck p xk. And we know that this is smaller than f of x star. So what is this expression? Right. Just give you a hint. So that's f of x bar. And from that we have that q star minus f of x bar is the limit k in k, ck p xk. What do we know about ck? It's diverging. This guy is a finite number. So what can we say now about p of xk? Right, they converge to 0. We know that also xk is converging to x bar. We assume that p is continuous. So p x bar is 0. So x bar is a feasible point.
So we did show that f of x converges, but where does it follow from that x converges?
So x bar was a limit point of those x's.
Right, but I have this mental image that you could, in some sense, like, I could imagine that the x's could not converge while it could diverge.
Yes, exactly. Yeah. So, but what we proved that this q star minus f of x bar, this is this expression here, right? So from this it follows that p P of xk is converging to 0, where xk is, so k is in this subset k. So xk is converging to x bar in this case.
It's an assumption.
Yeah.
If you go back to the previous slide, he assumes that xk converges to limit point.
So here, it's here. This is the assumption.
Yeah.
So this is how x bar is defined.
Is that a trivial assumption? Like, are there problems
So,
where xk could not
our assumption was that x bar is a limit point of those points that the penalty method generalizes. So the penalty method generalizes x1, x2, x3. Indeed, it might not converge, but it has limit points. X bar is the limit point of that. So it might happen that the penalty method, right, it gives x1, x2, x3, and so on. It's not converging, but I'm just saying let x bar be a limit point of that.
Oh, a limit point would be a limit of any sub.
Yes, exactly. So a subsequence that's converging.
And there's like some result in theory of spaces that there will be a limit point for subs.
Right, so x, right. Right, so our assumption just was that you have that. Is it clear now? Okay. Good question. Other questions? But indeed, we didn't discuss the properties of that limit point. We just assumed there's one.
What if ck equals to k minus 1 over k? In this case, ck is increasing, but it doesn't know if that works.
So ck is going to infinity, right?
K minus 1 over k.
So the assumption was, yeah, I just didn't get the question. So ck is going to infinity.
No, it's not going to.
Oh, that was our assumption.
Like CK is for us to choose. So
Yeah,
can
we choose.
any CK.
So it's here, assumption. This previous slide. This one. Okay? Right. So we need that assumption. Yes?
Some kind of incremental update rule from xk to xk plus 1. But otherwise, why don't we just assign ck to be a very large number and then solve one single problem?
Yeah, good point. Let me go back to that after we finish here. Okay? So it's just I just want to know if the proof is clear now.
So how do you get a second line limit of that?
Right, so we are here. We know ck is going to infinity. From that, it follows that p of xk is going to 0.
I mean the second line, right below the box.
So let this one. Oh, f is continuous. Right. So we assume everything possible that simplifies our life. Okay. Other questions?
I mean, if f is not continuous, we don't even have a convex.
Yeah. So f is continuous. Okay. So so we know x bar is feasible. We also know that f of x bar, if you look at this, f of x bar is not bigger than f of x bar. But x bar was the optimal solution of primal. Now we have x bar, which is smaller or not bigger than x star, and x bar is feasible. From this, it follows that x bar is an optimal solution as well. So can I draw this? Okay, so there was a question about why we don't choose a big enough C, right? And because what happens is that the bigger the C, usually the more difficult this problem is to solve. If you just choose a huge C, your original problem is basically equivalent to your primal problem.
Xk would be a starting point.
Exactly, yeah. So you solve a small, easier problem. From that, you have a guess, and from that, you start solving a more difficult problem. And that's also a good question: how you should choose CK, and people just come up with different heuristics, like let it be polynomial or something, diverging to infinity. Yeah, good point. Okay, so let's move on a little bit because, yeah.
This method just proves consistency. I mean,
Exactly.
When large C, I mean, even if you chose a very large C, you're not, I mean, it's not going to be the solution to your problem.
Yeah, so that's a good point. So if you just choose one big C and solve that, usually that's not a solution of your original problem. Usually. But in your homework, you will see examples when it's a solution as well.
Is there a rate of conversion?
Once again?
Is there a rate of conversion? Something like
So we didn't discuss that yet, right? Okay, so the class is almost over, and I finished 1/3 of what I planned. So so here are a few of commonly used penalty. So as we discussed, people sometimes just use the positive part of your function gi and put this to some polynomial. If q is 1, this is linear penalty, and quadratic penalty is also often used. It's just this. Okay, some notations. So I will just say g plus I to denote the maximum of 0 and gix. And g plus x will be a vector of all these g1 plus and so on gm plus. And using this notation, some penalty that are often used is p of x is just the square norm of g plus, or sometimes people even put a gamma positive definite matrix between these two vectors. Okay, I just keep this. Okay, so in algorithms, so now we know what the penalty program is. It's just xk is f of x plus ck px, right? And that's the penalty program, and the penalty function is gi plus is again the maximum gix right. And for penalty, what we will use, that is just a gamma function of g plus x. And for example, if we use the quadratic penalty, that this is just y transpose y. We will assume that f is differentiable, g is differentiable, and and p is differentiable as well. So what we will need, that f1 is continuous differentiable, g is continuous differentiable, and the penalty is continuous and differentiable as well. The problem that we will have here, though, is that if you look at how the g plus is defined, there's a maximum there. And we need to calculate its derivative. So it will cause some complications, but we will put that to a gamma function. And you can prove if this gamma is polynomial and q is bigger than 1, then this p, you can calculate the derivative of this p even though there's a maximum function inside of this. So we will got a function where we can calculate the derivative. After this, we will not have constraints, so we can just use the traditional unconstrained technique. So we can use Karush-Kuhn-Tucker theorems and so on to calculate the minimum of f. And I think this is where I'm going to continue next time.